All right, this week we're talking about section 4.5. This is the second to last section in this book that we're covering. It's an application of the definite integral called average value. Averages are something that you have seen before. It's a familiar concept. And when we talk about finding an average of a set of numbers or a set of numerical data, most of the time we're referring to a specific type of average called a mean. There are more interpretations of the word average. If you take a statistics class, you use the terms measure of central tendency, and there's different ways of interpreting that. But the mean is what people typically are referring to when they say an average of a set of numbers. So if you have a set of numerical data, let's say y1, y2 through yn, you have these n values. Each one represents some number. Okay, if you want to find the average of this set of numbers, the trick is to add them all up and then divide by how many there were. In this case, it would be y1 plus y2 plus so on and so forth all the way to yn, all divided by n. That would give you a number that falls somewhere around the middle of all of the numbers in the set. A number that would be less than the greatest of these numbers, if they're not all the same, and greater than the smallest of these numbers, again, if they're not all the same. So that's great, and that's very useful, but there's sometimes applications where the number of values that we're trying to average is actually infinite. And that might seem impossible at first, because if you're trying to take an average of an infinite number of numbers, not only do you have to add up infinitely many values, but then you have to divide by infinity, and that doesn't make sense. That's actually not possible because infinity is not a number at all. So as we have seen in this class, anytime we want to work with infinities, we're going to have to apply a limit somehow. So we want to construct this concept of an average value of an infinite number of numbers by using limits. And we're going to be careful about how we do this. So the first thing I want to address is where these values come from. Let's interpret these values, the y1, y2, and so on and so forth, as the outputs of some function f of x. So each of these y values is equal to f of some number that we plug in for x. So if we take that function, and let's suppose that our function is defined on some interval, closed interval a, b, and it's specifically the average value of our function over that interval that we're interested in. We can start with an approximation of that absolute value by doing this process. We can take this interval, we can cut it up into a finite number of subintervals, let's say n subintervals. And then from each of those subintervals, we can pick exactly one number that lives in each subinterval, and let's call them x1 star, x2 star, all the way up through xn star. So x1 star would have come from the first subinterval, this x2 star came from the second one, and so on. Okay. Next, in addition to that, we're going to assume that we defined, or we cut our subintervals up into equally sized subintervals, which is typically what we do when we do this. We've defined definite integrals this way, and the width of each of those subintervals we're going to call delta x. We've already talked about how to find delta x. It's just the length of this interval, which is b minus a, divided by the number of subintervals, which is n. Okay? Now, how do you find the average of this sample of n numbers? Well, remember, it's not the x's that we're taking the average of. It's the outputs of our function when we plug these numbers into our function. We're only interested in the outputs. So I would find f of x1 star and f of x2 star and so on and so forth. That would give me a total of n different numbers as outputs. Then I would add them up and divide by n. This is the definition of an average, right, or a mean. However, that n right there shows up in the equation for delta x. So notice, if I have delta x equals b minus a over n, I can multiply both sides by n and then divide both sides by delta x, and this shows that n is equal to b minus a over delta x. So if I use this as a replacement or a substitution for this n right here, I get this expression. f of x1 star plus dot, 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 all the way up through f of xn star over this fraction, b minus a, over delta x. When you divide by a fraction, that's the same as multiplying by its reciprocal. So I can think of multiplying this sum by delta x over b minus a, which I'm splitting those up here and putting the delta x here, and then just leaving a 1 over b minus a there. Okay? If I distribute that delta x in, I get expressions like this that are being added, and this can be written in summation notation this way. This is equal to 1 over b minus a times the sum from I equals 1 to n of f of xi star delta x. Okay, remember, as a Riemann sum, these would each represent the area of some rectangle. Now, like we said, this is just an approximation, but as I alluded to earlier, we're going to take some kind of a limit as n goes to infinity to take this average from the average of a finite number of values to an infinite number of values. So if I take the limit as n goes to infinity of this thing here, which represents that average, remember 1 over b minus a would be a constant, and that can be pulled out of your limit. And then the limit of that Riemann sum, by definition, is a definite integral. And this thing right here is how we find the average value of a function over an interval. So if you want to find the average value of any function now, it has to be a continuous function, but any function f of x over the interval a, b, what we do is we integrate it by, or from a to b, so that's the interval, and then we divide that answer by the width of the interval ab. And that's it. So let's try an example. I want to find the average value of f of x equals x minus 2x cubed on the interval 2, 4. So 1 over b minus a, this is b and that's a, 1 over 4 minus 2 times the integral from 2 to 4. Notice I'm using the endpoints of my interval here. And then I have x minus 2x cubed dx. Okay, this is equal to, that right there is 1/2, so I have 1/2 there, times 1/2 x squared, minus, this would give me 1/2 x to the 4th, from 2 to 4. I can start evaluating the 2 and the 4 here, but one thing I think I kind of like to do, I see a common factor of 2 there, or 1/2. I'm going to pull that out. It multiplies to the 1/2 that's already there, and now I get 1/4 with an x squared minus an x to the 4th here. Again, from 2 to 4. What is this equal to? Well, it's 1/4 times 4 squared, which is 16, minus 4 to the 4th power, which is 256, minus, what do we have next? 2, let's put parentheses around this, 2 squared, which is 4, minus 2 to the 4th, so that would be 16. Okay? All right, so 4 minus 16 is negative 12, but this negative will make that positive, so I have 12 plus 16. 12 plus 16 would be 28 minus 256. And I could do the subtraction here, but I'm going to do a little trick. If I multiply the 1/4 in at this point, I can divide both of these things by 4. That's going to become 7 minus, and then 1/4 of 256 is 64. 7 minus 64 is going to be negative 57. Whoops, there we are. That is that average value. Okay, now, what would this look like graphically? So this is kind of something off to the side here. Suppose we graphed our function, and this isn't necessarily this function, but just some other function, right? If I graphed my function, something like this, and maybe this is the interval from A to B. You notice on this interval, I've got some high points and I've got some lower points. The average value, which I'm going to just call it average, like that. In fact, normally we call it f average. So if this is y equals f of x right here, it's some number that's somewhere in between the y values that I'm getting for my function on this interval. Somewhere in there, right? Now, from the definition for average value, you notice that when I make this dashed line, I get a rectangle right here. The definition of absolute value or average value implies that the area of that rectangle is exactly equal to the area under the original curve from A to B. So geometrically or graphically speaking, that's the connection between these concepts. Let's try some more. Let's try this one. It's a more complicated looking function. I want to find the average value of g of x equals x plus 1 times the cube root of x squared plus 2x on this interval. Same concept. 1 over 4 minus negative 3 times the integral from negative 3 to 4 of x plus 1 times the cube root of x squared plus 2x dx. So this is the same idea, but the function is much more complicated looking. So when I see this, I imagine a u substitution would help. And oftentimes when we've had something underneath a radical or in parentheses, choosing that as our u has been the way to go. I'm going to set u equal to the expression that's under the cube root, x squared plus 2x. Okay, if that's the case, then du would be equal to 2x plus 2. Now compare that expression to the part of my integrand that's outside of that radical. I have an x plus 1 there, and I have a 2x plus 2 here. This is exactly 2 times this expression. So if I multiply both sides of this by 1/2, I get 1/2 du equals just x plus 1. So, I forgot my dx though. I'm going to include my dx in there. This is how I get those things to match. Okay, so now let's take a look at what this turns into. 4 minus negative 3 is 7, so I'm going to have a 1/7 there. My integral, I'm changing my limits of integration because I'm using a u substitution here. So I'm going to plug negative 3 into my u. Negative 3 squared is 9, plus 2 times negative 3, that's negative 6. 9 minus 6 would just be 3. Plugging a 4 in, 4 squared is 16, plus 2 times 4, that's 8. So 16 plus 4 would be 20. So I'm going to put a 20 there. Okay. Then I have a cube root of u, which I can write as u to the 1/3 power like that, times du. Okay. This is equal to 1/7 times, so adding 1 to this would give me 4/3. Multiplying by the reciprocal gives me 3/4. And then I'm going to have u to the 4/3 here, 3 there, 20 there. Okay. Now thinking through what this means, I'm taking the cube root of a number and then I'm raising it to the 4th power. In this case, if I plug either a 20 or a 3 in, neither of those have a nice cube root. So rather than try to evaluate that exactly, I'm going to leave things in terms of that rational exponent. Let's do something with the fraction here, though. I'm going to bring the 3/4 out. It multiplies to the 1/7, and I get 3 over 28. And then when I do this step, I'm plugging a 20 in, and I'm going to get 20 to the 4/3 power minus 3 to the 4/3 power. And I'm fine just leaving it like that. If you really need a decimal, you could go to a calculator, but we're not going to try and simplify that any further. Okay? All right, let's take a look at another average value problem, but phrased a little bit differently. So notice the wording in this one. Find the average rate of change of f on the interval 1, 3 if f prime of x is equal to 1 over x minus 5x squared. So there's two functions being referenced here. There's f, but then there's f prime, and we don't know f. but we do know f prime. And if you notice what it's saying, it says find the average rate of change of f on the interval. It's not finding an average value of f, it's an average rate of change. We know that the derivative is the rate of change of f. So what this is actually saying is find the average value of this derivative, which we have an expression for, on that interval. So understanding the wording here matters, but now we can see that this just reduces to this problem. 1 over 3 minus 1, there's the fraction on the outside, times the integral from 1 to 3 of this. So I have 1 over x minus 5x squared dx, and then go ahead and integrate. This becomes 1/2. 1 over x, we know we get a natural log of the absolute value of x. However, the numbers I'm plugging in are already positive, so I don't need to really concern myself with the absolute value here. Minus, add 1 to the exponent and then divide by that. So we get 5/3 x cubed from 1 to 3. Okay, so let's think through this one. I'm going to get 1/2 times the natural log of 3 minus 5/3 times 3 cubed. And then we're going to subtract from that the natural log of 1 minus 5/3 times 1 cubed. Now there's a convenient technique you can use here. Instead of cubing the 3 first, notice that I have a 3 in the denominator here. There's a little cancellation that happens. I can cancel this 3 with one of these 3's. That means now I have 3 squared. So let's simplify this a little further. I have 1/2. The natural log of 3 is not going to be able to be simplified any more than it is. You can plug it into a calculator, but then you're rounding a decimal. And as we've said over and over again, we prefer to just leave things in terms of logarithms if it's going to be between that and a rounded decimal. I've reduced this to 3 squared, which is 9 times 5. That's 45. So I have minus 45. The natural log of 1 is 0. So we know that much. And then here I have negative 5/3 times what's going to be a 1. Negative 5/3, but then this negative will come in here and make that positive. So plus 5/3, like that. Okay. To get a common denominator here, 45 times 3 is 135. I have negative 135 plus 5, which would be negative 130. This becomes 1/2 times the natural log of 3 minus 130 over 3. And this is a fine form to leave my answer in. I don't need to really do anything more with that, but that is the answer for that one. Okay. All right. Next example. We want to find the average value of f on the interval -5 to 0 if f prime of x equals 4e to the x minus 3x squared, and the graph of f passes through this point, 0, -2. So the tricky thing about this problem is, if you notice, it looks similar to the previous one in that we're given f prime, but it's not asking for the same thing. The last problem asked for the average rate of change of f, which meant we could just use f prime as our integrand. Here it's saying find the average value of f on this interval, where we don't know what f is, but we do know what f prime is. So we actually do need to use f as our integrand, but we don't have it. We only have f prime. So what I'm going to do is I'm going to find an antiderivative. This is not a definite integral that we're doing. It's an indefinite integral. I want the antiderivative of f prime of x, because that would give me a candidate for f of x. Okay, I'm going to differentiate or take the antiderivative of f prime. So that's 4e to the x minus 3x squared dx. This is an easy antiderivative to find. It's 4e to the x, that's its own antiderivative, minus x cubed plus c. Remember, we have to have that plus c. Now, without knowing what c is, I can't go any further. But that's where we use the rest of this information. Remember, we have seen this kind of thing before. So when I have this point on this curve, I have an x value and I have a y value, or an output. I can plug 0 in for the x's, set it equal to -2, and then solve for c. So if I plug a 0 in for x here, e to the power of 0 is 1 times 4, that's 4. 0 cubed is 0, so I'm not going to bother writing that. And then I have plus c. That's equal to negative 2. Subtracting 4 from both sides, I get c equals negative 6. So f of x is equal to 4e to the x minus x cubed minus 6. Now that I know what f of x is, I can find the average value of f of x over this interval. So we do that part next. 1 over upper limit minus lower limit, so 0 minus negative 5. By the way, because we're always finding the upper limit minus the lower limit here, this fraction should always come out positive. Even though there's negative numbers in there, it's always going to be positive in the end. So that's a good way to check to make sure you're doing things correctly. The interval goes from negative 5 to 0, so those are also my limits of integration. And let's look at the function that we're integrating. 4e to the x minus x cubed minus 6 dx. Okay, so now that I have this, let's find our antiderivative. This is 1/5. 4e to the x is its own antiderivative. This is going to give me negative 1/4 x to the 4th, and this is going to give me negative 6x, from negative 5 to 0. Okay, now when I plug a 0 in, let's see what happens. Got 1/5. So again, e to the 0 is 1 times 4, that's 4. In these two terms, when I plug a 0 in, both of them go to 0. I'm not even going to worry about writing that. Let's just write what's left. So now we've got negative 4e to the negative 5th power. Remember, put parentheses around that. Minus 1/4 negative 5 to the 4th power minus 6 times negative 5. Okay, and we just need to work this out. So one thing I'm going to do that's going to save me a little bit of trouble, I'm going to distribute the 1/5 in right now. And the reason why is it's not going to help me with these two terms, but I'm going to be able to cancel, some of what's going on here. So notice if I distribute that, I'm going to get a 4/5. Distribute this minus sign in, I'm going to get negative 4e to the negative 5th times that 1/5. It becomes negative 4/5 e to the negative 5th. Here, negative 5 to the 4th power, because it's an even exponent, that would be a positive number. But then I'm multiplying it to a negative, and then I'm bringing another negative in. So all that combined means this is going to come out positive. And it's 5 to the 4th power, but when I distribute this 1/5 in, that'll cancel with one of those 5s and give me the equivalent of just 5 to the 3rd power, which is 125. This becomes plus 125 fourths, okay? Finally, this 5 will cancel this 5, but that minus is still left behind. So I have a minus times a minus, which is positive, but then another minus distributes to make it negative again. Negative 6 is what I have there. Okay? All right, now at this stage, it's just a matter of taking these values and getting a common denominator, adding things up. I'm going to let you do that part on your own in your notes. You would want to combine these three numbers, but you would want to leave this one alone because it's not really a like term. It's got that exponential in it. I'm going to end this video here. We have one more example to do, but we'll do that in part 2.